Okay. Started. So yeah, right guys, good morning, good evening. So I am Nikshep, I am a coordinator in Horizon Club, and he is Avinash. So he's also a coordinator and he's a part of astrophotography team. So this session would be about intro into general relativity and black holes. Yeah, thank you for coming. We'll start the session. Okay. I'll do it for myself. I'll do it for myself. You can go, sir. You can go sit if you want.
You say.
Huh?
What you say?
You can go sit if you want. So right, in this session, I'll just tell you what we are going to be doing. So I'll introduce what is Minkowski space-time interval, and then I'll introduce what is time cones, and then we'll just look a little bit of GR. Why gravity is not a force, why don't we consider it as a force, and all the things. And then we'll start the black hole segment. So in the black hole segment, we'll just see what is event horizon of a black hole, and then some interesting events, interesting phenomena near the event horizon of a black hole. And then at last we'll be like seeing what is Penrose diagram, what is the basic idea of a white hole and a parallel. As a physics enthusiast, as we graduate from 12th, I have seen this common urge of everyone, just graduate from 12th and we're like black holes, time relativity, multiverse, come on, and this, something like this happens, the rook takers. So in this session, we would try to keep the math as minimal as we can so that you guys would understand. So if you were looking for a session where you would explore all these things and with the minimal math as possible, yeah, this is the session for you guys. Let's go. So So let me start with the common story. I know everyone would be aware of this right now. Let me say there are two frames, x dash t dash, and this frame is moving with a velocity v, suppose, right? So now let's say you are standing in this frame and there is your friend. So he throws a ball with a velocity u dash, suppose. So now what's the velocity of the ball according to you? U dash plus v, right? So let's consider it travels some distance. It takes t dash, some interval of t dash. So what's the time according to you? Time, it would be some delta t, right? You would see the same time. Now let's say instead of a ball, he projects light. So this person would observe the light going with a velocity c, suppose. So what would you see the light going with the speed of? Yeah, I know you guys are a little smart. Okay, let's stick on to the Galilean transformation aspect. As you have studied in 11th and 12th till now, you would you may assume that it travels with some c plus v, suppose. And there comes, this is the point where Maxwell equations come into play. So when you solve Maxwell equations, you know that speed of the light is 1 by root of, let's suppose they are in vacuum. You know this, right? So this is what we get after solving Maxwell equations. So we know that Maxwell equations are irrespective of frames. It's not referring to any frame. So this gives the idea that speed of light is constant. It doesn't vary with any inertial frame, right? So yeah, this was so that just proved Galilean transformations to be wrong. Duster. So right, So then Einstein came into the picture. So Einstein just introduced two things. Einstein said that speed of the light is invariant in all the frames. see, you are standing you are standing here. Let's say your friend is standing in a moving bus. So both of you will observe the speed of light to be constant. Speed of light doesn't change with inertial frames. And second thing is that introduce that nothing can go beyond the speed of light. I mean, speed of light is the limit of speed itself. That's two things which got plugged into the equation. And then now Galilean transformation proved out to be wrong. So there was a new set of transformation we needed. So that's nothing but Lorentz transformation. So yeah, this is Lorentz transformation. Right. I would want to discuss how this. So yeah, clearly we are not going to the derivation mass of it. But I would want to explain what does it geometrically mean. So to do that, I want to now introduce a new space-time coordinate system. It's called the Minkowski's coordinate system. So right. So what is Minkowski's coordinate system is that I would rather use a picture, let's suppose. In this axis, I would denote distance. In this axis, I would denote c and t. So c is the speed of light here. I mean, t is time. Why am I doing this ct? Because it simplifies us a lot of things. You would just see, it would just become obvious to you. Right. So yeah, before that, very quickly, I don't want people to look just what's happening while I look whenever I say space interval. So before that, so let's say any coordinate system, Euclidean, Minkowski, any coordinate system with some x1 here, x2 here. So how would you calculate the interval between any 2 points in a coordinate system? So it would be ds square is equal to summation of nij dxi dx. So yeah, anyone who knows contravariant, covariant vectors, please hear me on this context. I am not referring to any contravariant, covariant, just matrix notation. So yeah, we would. So for the Euclidean space, you have studied till now. I mean, x, y, the distance, the normal Euclidean space you have studied till now. This matrix was 1 0 0 1. So let's x1 is equal to x, x2 is equal to y. If you do that, I mean, all the summations where x and dx and dy comes, it just goes to 0, and you are just left with dx square is equal to dx square plus dy square, the Pythagoras theorem, right? So yeah, if you just get confused and not able to catch up at any point, just feel free to stop me at any point. So for Minkowski's coordinate system, yeah. Okay, what do you want? So yeah, so this is the formula for calculating interval between any 2 points in any coordinate system. So this is a metric, we call it a metric, right? So here it denotes the element of a metric. So this is the summation. So let's say n11 is 1. So I have defined dx1 to be x. So when I is equal to j, so dx into dx square. So when it is I not equal to j, it would just go to 0. I mean, the dx dy terms go to 0. So when I is equal to j is equal to 2, it would dy 1 dx square plus dy square, right, on the page. So yeah, for this Minkowski space-time coordinate, I would want to introduce a new metric, which is -1 0 0 1. So yeah, +1 -1 also works, but we'll go with this convention. So by this I can say that space-time interval would be minus c square dt square plus dx square. right? Because it's minus 1 when both are, okay, dx1 is equal to ct, x2 is equal to x. Sorry. So when it is both x, it's minus 1. When it's both ct, okay. When it's both 1, dct, and it's minus 1, minus a square t square, and it's other term gets cancelled out, that is dct into dx wala terms gets cancelled out in the summation, and it's dx square, it's 1 dx square, right? So I hope you're in the same page. So, and then why do I need this? Why am I defining this matrix to be this is? So the thing happens. So when I put this metric to be this becomes invariant. I mean, just like speed of light, it becomes invariant of the frames. I mean, I can say that ds square would be ds dash square for both the frames. I mean, one frame at rest, another frame is moving. So yeah, so I would take a main takeaway from this part, that is, when there are two frames, let's suppose this is moving with you are at this standing frame, rest frame, there is a friend moving with this frame, frame is traveling with a velocity c. So we know that two things are invariant here. What I mean is that, see, if both these people measure any length, he would measure one length, he would measure another length contraction. If they measure any time interval for any event, the moving frame wala guy, his clock actually ticks slower, time dilation. So there is only two things which are invariant here. The two things which both of them agree upon. One is the speed of light, right? Both of them agree upon that. There's no doubt about it. Second is what we have defined, space-time interval. So both of them would agree upon this. I mean, c dt dash square plus dx dash square is equal to minus c square dt square plus dx square. I mean, any doubts till now? These two things are invariant. This is what I would like to. Yeah. So now let's check upon this space-time diagram in more. So yeah. So now I would like to introduce. I would like to put a 45-degree line. So I can say that this is inclined to both of the lines. So this is like 45 degree. So I can say that in this line, x is equal to ct, right? So it just means that v is equal to c. So if I square on both sides and then take this part, I can say that ds square is 0. Space-time interval is 0 on this line, right? Agreed? So ds square is 0 on this line, right? So the thing is v is equal to c. So the thing is, this line represents the path of light. This line is nothing but the path of light. That's what I understand. So we would call it light-like intervals. So in this line, space-time interval is 0, right? So if I extend this, if I draw this would also be the path of light. Agreed? I mean, of course, here would be minus x is equal to ct, but we will square it. So we will square it on the both side anyway. So it would be minus c square t square plus ds square is equal to 0. ds square is equal to 0 on this line. So still, this is the path of light. Agreed? So now I would like to break down this graph into two regions, and then it would become obvious that why I did that. Let's say So see, first of all, in this graph, any point in the graph denotes an event. This is an event, this is an event. Any point here denotes an event. So if I say that to connect this event to any of the points here, I would need a slope which is greater than this line, space line, right? So it would just, I can say that in this region, C2 would be greater than X, right? So if I square it, I can say that ds square would be lesser than 0. Square it and bring it that side, ds square would be lesser than 0, right? So I mean, it would be the same, the sign changes, but we just squaring at the end of this, so it doesn't matter. So I can say that to connect this point, this event to any of the events in this region, I would have to have a slope which is greater than this line, right? So yeah, I would extend this. These are still the paths of the light. Okay. So yeah, leave that. I mean now this region, to connect this event to any of the points after this line, I would have to have a slope which is lesser than this line, right? So I can say that x here in this region is lesser than x here is greater than c, right? So ds square would be greater than 0. So basically the summary was that I just divided into two regions. One is the cone region where the space-like interval is lesser than 0, because see, we are anyway squaring this, it doesn't matter. So and this region where the ds in space and space-time interval was greater than 0, right? Any doubts so far? So right. So why did I even, so let's come, why did I even segregate this? So can you take a wild guess? I mean, this is the hint, this is the hint, this is the hint. Can you just take a wild guess why did I mean segregate the graph like this for in this type of two regions? These are two the hints. I mean, any wild guess? Okay, I would just go there. So I can say in other words that to this event, to any of these events connected here, I would have to have a speed which is, I would have to send a signal which travels lesser than the speed of light. Can I say that? And to connect any of the points in this region, I would have to send a signal which travels greater than the speed of light, right? So as we know that nothing travels faster than the speed of light, I can just say that this point can only be connected to any point which is inside this cone, right? Any doubts so far? Yeah. So right. So yeah, what do I mean two events to be connected? See, for two events to be connected, you always need a signal. I mean, that's what in simple words causality is. Like you are sitting here, let's suppose you go there. See, that's an event, that's an event. To be connected, you need a signal. The signal itself you. I mean, you're sitting here, you just ask your friend to do something and he does that. So, you asking him is an event, he doing it is an event. So, the signal you sent was through the air, the sound, right? So, I can just say that in simple words. So, this event to affect, to cause any, to be connected to any of the events here, you have to send a signal which is lesser than the speed of light. So I can say that this event can only influence the events in this cone, right? And then similarly this event cannot influence any other events in this region. So yeah, this is the same analogy here. To this point to influence this event, it should send a signal which is lesser than the speed of light. For this signal to be connected, it should send a signal greater than the speed of light. So as I can say that this point can only influence the events in this region, I can call it the future cone, right? And this is the set of points where only this is the set of points which can influence, which could have influenced this event. So I can call it the past point. And this region which neither this event can influence nor it could have been influenced, I call it nothing. I mean, it's just nothing. Right. So yeah. So that's what we defined the time cone. This is what a time cone is, a future cone and a past cone. So right, this was it. So yeah, the main takeaway was that, so you are sitting in this classroom, let this event. So your all possible events, I mean all your future possible events lies in this part of the cone. And all your possible events that could have influenced to come and sit here lie in this part of the cone. That's the past cone. And all the events neither you can influence, I mean which can happen in your future, nor it could have influenced you to come here, would lie in this part of outside the cone. That was the main takeaway from this. So yeah, before that I would just conclude, end this part of the session by saying what does the Lorentz transformation geometrically look. So let's, the same scenario where one frame is at rest, another frame is moving with the velocity v, suppose. He is your friend. See, yeah, this is a very, your friend which I am referring is a very sacrificial character. I mean, we just put him in some frames. We just throw him in some frames. At the end of the session, we would be like throwing him into black holes and then observing from inside, outside. So yeah, you can imagine him to be whomever you like, I mean, not like precisely. So yeah, so you are resting, you are in the rest frame, you are standing in a rest frame. How would your how would your world line look? It would be just this, right? Distance is 0, time is going. So I just want to look, how does his frame of reference, how does his frame would look according to your frame? See, this is the path of light. This is constant for both of you. So anybody would try to take a wild guess how his axis would look according to you. Yeah? Anyone? Fine. Yeah, I will just say it. It would be like this. Right? This just remains same for both of them. So let's say if he starts moving with some higher velocity, higher constant velocity, it would be just this. Right? So let's say it becomes light. I mean, it would just go and converge. I mean, that's what the intuition I just wanted to give you. So yeah, this ends this part of the session. I would like Avinash to continue. So yeah, this is the, see, we just saw a case where one frame is at rest, another frame is moving with some velocity in x direction. What if the frame have velocity components in all the direction? So this would the general Lorentz transformation look like. That's what. Yeah, you can start.
Did you explain time like it was? Okay guys, that is almost from SR, mostly from SR, and we are now starting the GR thing. What is SR, what is GR? Anyone thinking about that? SR is special relativity. That is from the special relativity. We are starting the general relativity from now on. Okay. First thing we need is equivalence principle. What is equivalence principle? It says that accelerating frames or non-inertial frames are indistinguishable from a frame which is standing on a planet or anything. Okay, let's say we have two frames. One is accelerating with some acceleration, let's say g, accelerating with g acceleration, and one is placed on earth. if you are leaving a ball, what do you think happens to the both? They both will fall at the same rate, right? And like if you are in either of the situations, you cannot tell unless you are seeing from outside or with let me clarify. If you are in a rocket which is traveling at g acceleration, and if you are in a box or frame which is on earth, you cannot distinguish between these two from any experiments. Like you cannot say where you are from this. And the next thing is inertial references are locally independent from freely falling. If an inertial frame is there which is staying still or staying with going with constant velocity, that is inertial frame. So that is as same as a freely falling body. Did you understand? Freely falling body from towards any gravitational field. If you are in a box which is going with some velocity, and if you are in a freely falling body which is going from top, like falling from sky, so you cannot distinguish between those two situations with any type of experiments. That's what the equivalence principle states. Did you understand? Yeah. And when you are, this is the best example for first thing. Okay, light is going curved, right? In the first situation, we are turning on a light or throwing a photon, and the frame itself is going, accelerating. So the light will curve. If we are in the box, you can say that light will curve like this. In the same sense, if you are placing a box and turn on the light, it will also go in curve. But like we cannot say, because we need so much big. Like here also light is going at light speed, so you need so much acceleration. That's when you can see the curve. It is going in curve. Also here also we need so much long room to, like, let's say long room and more gravitational field to see this thing. That's what saying that gravity can bend light. And proper acceleration. What is proper acceleration? Is the acceleration you feel is the proper acceleration. If you are in a car and going with accelerating, you must feel a pseudo force pushing backwards, and you must feel some acceleration. That's what I call as proper acceleration. And it is always be zero for an inertial frame, which is and non-zero for non-inertial frame. And it is like it cannot be changed with respect to the frame of references. If you are seeing from an inertial frame to like non-inertial frame person, he has proper acceleration not equal to 0 to you and to him also. Got it? Yeah. And he said that gravity is not like any other forces, because see, if you are pulling a car with rope or a giant magnet or the engine of car itself, you in these three situations you can feel a backward acceleration, proper acceleration. You can feel it is not 0. And if you are we are putting your friend and throwing him, like even in this situation your friend doesn't feel any acceleration backward, because earth is pulling you and your car and friend equally. That's why like proper acceleration is 0. He didn't feel any acceleration in that frame. This tells that gravity is not like any other forces. Oh, what? Yeah. Gravity is not like any other forces. Newton's first law says that if you are moving, if nothing stops you, any force, you tends to move. That's it, right? But we are like saying gravity is not a force. We need to change that a little bit. In absence of non-gravitational forces, a free test particle moves along a curve called geodesics of space-time. Geodesic means it is a path of a particle which is moving. That's it. How can I say it? If you leave any particle without any forces, if it is going in any path, that is called as our like geodesics. Like let's say Earth and like orbit, satellite on orbit. This satellite will go on and on if not any force is acting on it. This is called its geodesic. And if you like leave a ball here, it is going like this, right? So it is called its geodesics. The path a particle is going unless it has some force acting on it. That is what we call as geodesics. And in Newtonian physics, if apple is staying on the ground, we say that there is a force of gravity mg is acting downwards and a normal force is acting upwards. But in SGR, we say gravity is not a force. So its geodesic path is like this. It is going towards the Earth due to Earth's gravitation. But the molecular forces preventing it from going into that geodesic path, that's what we call it. If there is no normal force, what happens is it is going on its geodesical path. So we can say that there is F net is not equal to 0. In the GR, we say that if a particle is staying on the ground, F net is not equal to 0, because F net, like normal force is acting, which is helping the apple to stay there. If F net is 0, what happens? It is going on the geodesical path. Yeah.
So yeah, the main takeaway from that part of the session that in GR we are just considering gravity as not a force. That was the main part all of that was about. So right, next slide. So now Einstein field equations. I mean, of course, we are not going into the mathematical depth of it, but actually I would just explain what it just means. MKEUV. So the RHS part here, it just describes the distribution of mass and energy, and the LHS part here, it just describes the geometry of space and time. That's what it is about. I mean, we are not going to the mathematics of it, but maybe we are going to grill it and like derive it complete in a mathematical basis in the DC sessions. I mean, I wouldn't mind if anyone who is interested and can come and sit through the sessions. Wouldn't mind. So right. So what does this physically mean? So consider a space-time fabric. So what do I mean a space-time fabric? Like I was taking DC interviews, and then I asked the person about what is space-time fabric, and he was like, I asked the person, I was explaining about space-time fabric, and he was like, what is space-time fabric? I mean, how does this look like? I mean, where is it? I mean, please don't confuse it with yourself. I mean, what I mean space-time fabric is that I just drew a Minkowski's flat. This is a flat space-time coordinate system. If I add y coordinate and then I add z coordinate also, that's a 4D graph, right? See, x and ct, you will add y here, and you would also add z direction, z coordinate. So that's basically a 4D graph, right? So if I draw the geometry of space-time in that 4D graph, that's what a space-time fabric is. So what does this equation actually physically mean? So it just means that any mass in the space-time fabric creates a dent, creates some dent. You can see in the pic. So I mean, this is not the perfect way of saying that, because this itself is a 4D one, but actually this is the best way to represent that. So any mass dents the space-time fabric, and then the curvature of the space-time fabric which it has been dented, that's actually gravity. So let's say sun. So sun creates a dent in the space-time fabric, and all the objects, I mean, let's say planet, asteroids, I mean even light, which is moving in the gravitational field of the sun, actually it's moving in the curvature of this dent. So the normal question that would arise is that, you know that light travels in a straight line, right? I mean, the most natural question is that where is this curvature coming from? So I would like to give an analogy that, so let's say you are on the equator of the earth and your friend is also in the equator of the earth, suppose, and both of you started traveling in a path which is perpendicular to the equator, right? So I mean, at the paths which are perpendicular at the equator, so according to, in respect of both of you, you are just moving in a straight line, right? You are just moving in a straight line, but you are moving in a straight parallel lines because it's perpendicular to the common line. And the myth of the parallel lines never intersect, but you would just meet him at the pole, right? So that doesn't mean that they weren't traveling in the straight parallel lines. That just means that the path in which that paths were, the dimension in which that paths were was itself curved. So two parallel straight lines in 2D, they did intersect. It just means that the next dimension, the 3D dimension, was curved. So let's say there's a rocket. The rocket is moving with some constant velocity, which is greater, and then you have a ball, you just leave it beside you. So what do you expect? The ball to travel along with you, right? You are traveling, you will have a ball, you just expect that ball to come along with you. Now let's suppose that this spaceship was itself Earth. The spaceship was itself Earth. I mean, now you leave the ball, it would just consider this you and spaceship Earth as one body and the ball as another body. You leave the ball, it just comes and touches the Earth, right? So two lines in 3D, which was supposed to move in two straight parallel lines, they got intersected, just means that the next dimension was curved. So the main conclusion is that light travels in a straight line. There's no doubt about it. But the thing is, the path in which light is traveling is itself curved, right? That's the main takeaway of it. So this equation the main conclusion is that geometry of space and time is equal to the distribution of mass and energy. That's the main conclusion of Einstein field equations, right? So
So the most awaited parts comes. Do you guys are waiting for anything? For what? Black holes. Yeah, I know it is very curious thing. So what is a black hole? It is a boundary where anything can enter but cannot return. Even light itself, which is going at the speed of light itself. So anything can enter but nothing can escape from it. And there is two types of black holes. One is stellar black hole. Stellar black hole is like when 20 to 30 times of mass of a sun, a star which is massive 20 to 30 times mass of sun, when it dies, it becomes a black hole. If it is like less than that, it will become neutron star. If it is even less than that, it will become white dwarf star. These things are like my session only. It is summer school session. If you want to know what is star is dying or all that thing, you can go and check in Horizon Sky YouTube page. Yeah, and the next thing is supermassive black holes. We don't know how they form, but we can see them in every galaxy's center. Our galaxy also have a black hole. This is it. This is the first image of a black hole we can take. I expect some question. How can we take a photo of a black hole which doesn't emit anything, right? What? Not radiation, but it has like some disc thing. You can see in like, did you see Interstellar? Yes. There you can see the rings. That is not actually rings, like that is the dust or something. That's it, right? Yeah, this is the Sagittarius A. Its name is Sagittarius A. It is in our own Milky Way galaxy's center. And the gravity is so strong that it creates a pit. Like if you take an earth, it is not earth, it will bend the space-time a bit like this. And if you take our star, our sun, it will bend like this. If you take a neutron star which is massive than our sun, it will be like this. If you take a black hole, it will be like this. It seems like there is no end there. Like the space, it is not exactly how the space-time looks like. It is the representation of space-time in 2D. Yeah. Did you remember this scene when from Interstellar, when he is falling into the black hole? Do I need to tell?
We will skip that part because that's not. I don't know that's
Yeah. Okay. Sorry. Like there is another effect called spaghettification. Did you ever heard about it? Spaghettification. Like when you going near to the black hole, if your friend, we are throwing your friend into a black hole, when you are throwing him, the this part, like the parallel, in the parallel direction he will get stretched, and in the every other directions he will get squeezed. That is what we call as spaghettification. You will tell about that. Yeah.
So, just the spaghettification just means that you throw a body and then there is tidal forces, it just gets stretched away. I mean, okay, the question is that you saw a clip, why didn't he get spaghettified? Is there any, can you take a wild guess? I mean, you saw Cooper falling into the black hole, he didn't get spaghettified. So the thing is, the movie makers thought that it would be better kicking him into a supermassive black hole. I mean, supermassive black holes are actually very large, so the tidal forces would be negligible. So I mean, when there is a smaller black hole and there would be more stretching because of the tidal forces, and there's larger area, so there will be less tidal forces. That was the simple analogy of that. Tidal, yeah, I think I would get, yeah. So right.
You will explain later. Right?
So, leave that part. Let's talk about solving Einstein field equations. So, what do I mean solving Einstein field equations? So, where is that? Yeah. So the thing is, what do I mean solving Einstein field equation? So this part, this is the energy momentum tensor. So I just give the input in here. So I would just describe the distribution of energy and mass, and I would solve the RHS to get the metric. So yeah, if you remember the last G2G session, the slogan was, the main takeaway line was, metric is the king. Always trust the metric. So yeah, we are just giving the input in the RHS, solving the RHS to get the metric. That's what solving the Einstein equation is about. So yeah, this metric that we just saw, which is ds square is equal to minus c dt whole square plus ds square plus dy square plus dz square, where the metric was minus 1, 1, 1. We just saw it at the start of the session, right? So this metric is just the solution of Einstein field equations in the absence of any matter, or energy, right? So now we would try to solve the Einstein field equation for a single symmetric spherical body of some radius r. So we just solve the Einstein equation to find out the geometry of space and time around a single symmetric spherical body of radius r, right? So yeah, so in this, while we solve this, there are two cases. When it is uncharged, charged, rotating, non-rotating. So right, so a single body can be uncharged, charged, rotating, non-rotating. So we'll just, part of this session we'll just see this part of we'll just see the solution for Einstein field equation for a single symmetric spherical body of radius r, which is non-rotating and uncharged. So this solution is called square-shaped solution. So yeah, this is not a black body. This is not a black hole. For reference, this is not a black hole. This is any body, any spherical body. This solution here, we know that the solution of this, when it's describing a black hole, is a special case. I would just say that black hole is a special case of this case. So we would just look into when this solution, actually when we get to know that this solution is actually talking about a black hole. So right, so of course we are not going to see the mathematical detail of it, but I would just want to give a a logical analysis of how we derive the metric. I mean, so yeah, this we are solving this for a we are how many of you guys are doing PH 1010? PH 1010 course. PH 1010, you guys. 1010. So you must be knowing about what is spherical coordinates, right? So yeah, anyone doesn't know. So we are going. I am assuming that you know spherical coordinates. I mean, so we are going to solve this metric for a in spherical coordinate system. I would say GTT, GTR, GRR, G theta theta, G phi phi, GRT. So, see, I am not deriving the metric again in the normal convention way. I am just giving a logic of how it is. So, right. So, I can say that we are looking for a spherical symmetric body. So, around the geometry of space-time around that body, if I reverse the time, I shouldn't see the metric changing. I just mean that when I reverse the time, Tx. Yeah. So again, what is E? It is just the base dot product of the basis vectors. So yeah, please bear with the math. I mean, we would derive some very cool results at the next part. Just little bear with the math. So this metric is just a dot product of the basis vectors. That's it. So when I reverse the time, so this minus comes out. So I want the metric not to change when we reverse the time. So I would just say minus GTX is equal to minus of that. So I can to be such that, so I would just have to have this GTX matrix 0, right? So this would become 0. So and I want a solution such that, see, we are looking at a spherical coordinate system. So this is the radial coordinate. I want this radial coordinate to be perpendicular. We are looking at the spherical coordinate. I want this radial coordinate basis to be perpendicular to both angular bases. So to be that, we know that that's a dot product, so it should be 0. I mean this, wait, a G, this would just be 0, right? And then I want spherical symmetric. I want symmetry in spherical coordinates. I mean, the same thing, as I reverse time, if I reverse the angle, I don't want my metric to change. So I would just go with this to 0. So right, yeah. So after solving it for the diagonal elements, I would just get the metric as -1, 1 minus 2 gm by c square r 1 minus 2 gm by c square r minus 1 r square since. So this is the final metric for the square sheet solution. See, I just explained that for a metric of -1, 1, 1, how do we define the space-time interval, right? So in the same way, this would be the space-time interval for a square sheet solution, for in square sheet solution. So yeah, for all this, for the next part of the session, I would just consider radial motion. So I would just throw a particle into the black hole, and I would just want it to move radially into it. So this is the angular part. So this just goes to I mean, don't consider it for the next part of the session. That's what I would want. So yeah, what is event horizon? So the general definition of event horizon is that it's the boundary of two set of points. One set of points can send signal to infinity, and another set of points can't send signal to infinity. That's the general definition of event horizon. So this happens whenever this metric goes to 0. I mean, why this metric goes to 0, we'll just see it. So 1 minus 2 gm by c square r goes to 0. This is what I would want. So I can say that r is equal to 2 gm by c square. Is it fine? So yeah, this is called the radius of the event horizon for any body. This is the radius of event horizon for any body. So now let's say now we'll see when does this solution actually talking about a black hole. So when the radius of event horizon is lesser than the radius of the body itself. I mean, I repeat, when the radius of the event horizon is lesser than the radius of the body itself, it's a normal body. So yeah, would you like to take a guess what would be the radius of event horizon for Earth? For Earth? 2 centimeters. Any other guess? Actually, it's 3 millimeters. Yeah. So whenever the radius of the event horizon is greater than the radius of the body itself, it's actually talking about black hole. So in context of black hole, I would define the event horizon as a boundary. If you enter the boundary, you cannot ever return. That's the definition of event horizon in context of black holes. So graphically, it's just, we know that black hole creates an infinite dent, right? And the boundary in the dent where the infinite slopes get started is the event horizon. That would what graphically it means. So yeah, some interesting events about in which happens at event horizon. So we defined that ds space-time interval for light is 0, right? We just defined the space-time interval for light is 0. So if we just substitute the same there and then do some substitution, so we would get, so yeah, we are talking about light, just a caution, we would get dr by dt is equal to plus or minus c by 1 minus 2 gm by c square r. So this is the case for light. So you can see as r tends to the radius of event horizon, we can say that we just observe that dr by dt goes to 0. So yeah, so dr by dt. So when we are talking in relativity, we have to keep in mind with respect to what we are seeing. So actually the t here is the time according with respect to a observer at infinity. So dr by dt goes to 0. It just means that the velocity of the light with respect to an observer at infinity is 0. I mean, the takeaway is that, the conclusion is that light appears to be frozen at horizon to a distant observer for a distant observer in infinity. Right. See, light itself doesn't freeze. I mean, it appears to be frozen with respect to a person at infinity. So the light itself isn't freezing. So you can now we just saw the black hole image, right? So you can now relate why it's black in the middle. I mean, why the light appears to be frozen around it. That's one part. So that's one of the event. So another event I would want to say is that, so consider this equation. So yeah, so see, in this we are considering c is equal to 1 as a normal convention. If you ask why, I would not like to answer it because I don't want to deviate from this part and go to the, so the thing is, if you take the derivative of this equation 2 times with respect to proper time, I mean, see, when I say proper time, so what I mean by proper time is that, so observer, so So any observer moving, if he carries a clock and he measures the time, so the time measured by a moving observer is called proper time. That's it. That's in simple line. So yeah, we'll like kind of skip the computation here. So when we take the derivative of the squared circle solution with respect to the proper time, we would see that d tau by dt is equal to root of 1 minus 2m by r dt for a stationary observer, c square. Yeah. So you can again see that when r tends to the radius of the event horizon, we can see that d tau by dt goes to 0. So what I mean d tau by dt goes to 0, it just means that the proper time with respect to the time of a observer at infinity, it's going to 0. So basically it is, if you throw a clock radially into the black hole, so you can just say that as it approaches black hole, you will just see that the clock appears to be ticking slowly, and as it reaches event horizon, you would just see it to be stopped. I mean, it would just get freezed. I mean, you will never see anything crossing the horizon. That's what my point is. So see, the confusion is that the body doesn't, with respect to itself, the body itself doesn't get freezes at the horizon. It's just that with respect to you, where you are standing at infinity, you would just see that the time of the body is running slowly, and at event horizon it completely stops, and then you would never able to observe it cross the horizon. That's what the main result was about.
Yeah. Now let's throw our friend into black hole. Yeah. Okay. For safety precautions, we are seeing it from infinity distance. Okay. While you are seeing your friend is going closer and closer, their clocks, for him, their clocks, for us, their clocks seem to be tick slowly. As he said, it is due to time dilation, which is not by velocity. Even if you go faster, almost at the speed of lights or something, you can feel the time dilation. You can see the time dilation. But here, the time dilation is due to gravitational forces. And the light, he is a test subject, so he took a torchlight and pointing towards us. So while he is going into the black hole, the light seems to be redshifted. Redshift, do you know? Yeah, redshifted. And at the event horizon, the redshift becomes infinity. So if the light he is showing us light, the light looks like dimming and at last it will become a dark. Next. Okay, now let's see his point of view, not ours. In his point of view, let's say he has this time cone. He said time cone, right? This is the future cone. This is possibility of all his future events. This is the past cone. What can influence him? This is what he can influence. Okay. As if he is far from the black hole, it is normal that future cone is upwards and past cone is downwards. And while he is going near to the horizon, event horizon, his cone tilted towards the horizon a bit, and it is also getting narrower. He said like narrow towards the singularity. Singularity is nothing but a center of the black hole. Next slide. At the horizon, if it is I will show it. If this is the black hole, at the horizon his time cone became like this, like this. So what we can say is his all future events will be inside the black hole, so he cannot be returned. And after he is entered into the black hole inside the horizon, this is singularity. After he is entering, his future cone completely turns towards the singularity. So his future cone will become like this. This is future cone, not this. This is future cone. Its future cone completely towards the black singularity, and it is getting narrower and narrower. If he is here, future cone gets narrower. He is going nearer to the black hole, the future cone becomes alive. So we lost him. That's what happened when we throw our friend into a black hole. Next slide. So around the black hole, if we see, that's a 4D graph. If we draw it in a 2D graph, we just convert it into try to draw it in a 2D way. This is the radial coordinate. I mean, you can. So as we are only considering radial motion, you can consider it to be the distance, and this is the time. So this is the event horizon. That's the singularity. So you can see one thing. See that the light cones. I mean, see, all these are the paths of light. See, all these paths of light, you can see that they are converging into the horizon. I mean, converging into the horizon and also converging into the singularity. Actually, but theoretically, all the parameters of proper time and everything, it's well defined in horizon and it's not defined in singularity. I mean, that's why we call it singularity, because the parameters aren't defined. But the graph here shows a fake singularity at event horizon. I mean, say I would say this, that the analogy that I would want to give is that this is a globe. I mean, if we draw the globe on a 2D map, let's check your geography. I mean, here is Australia, here would be Greenland. So in a 2D map, you would always observe Greenland to be very much has a greater area than Australia, right? But actually Greenland is like some 20% of Australia actually. So why is this happening? Because you are drawing the 3D graph in the two dimension. So whenever you draw a higher dimensional graph in the 2D dimension, you would always end up in some error in the coordinate system, some error. I mean, so the thing is, you can always change the error by changing the coordinates itself, right? Nothing, right? So now if I just redefine the coordinate system, the y-axis and r-axis, let r-axis remain the same. I would just define the y-axis to be something which has t in its parameter. So this is called Eddington-Finkelstein coordinates. So that problem was kind of resolved. I mean, see this part of this segment, this ray of light, it goes down, it doesn't converge anywhere in the horizon, it just crosses, bends and reaches singularity, it converges in singularity. I mean, and this ray of the light, you can see that when as it approaches the black hole, it starts bending here, and it just completely bends this direction after it crosses horizon, and then it just converges in the singularity.
I mean the fake singularity wala problem was kind of resolved in this coordinate system. That's the thing. And then but still I mean, see, normally we defined the time cone to be 245 degree and 135 degree wala line, right? So we this was the proper time cone we defined earlier, but see, this time cone is fine at the regions which is far from black hole, but I mean as you go near black hole, it's kind of stacking. I mean, you can see it gets stacked and then everything is distorted. I mean, it's such a chaos there. So I would now want to introduce another coordinate system where we would try to keep this shape of time cone as it is. I mean, I don't want to change that. So yeah, after now, so yeah, I would not be going into the mathematical detail of it, but physically, if I were to explain, I can explain like this. See, this light is bending as it reaches here. So I can say that if I hold this, see this ray of light, forget that ray. This ray of light are bending as it reaches. So I can kind of imagine that if I hold this sheet of paper and then I would just rotate the lower part of it, and then these are little bending. So if this part of the paper, if I would pull it there, that I mean, see, these are bending, right? So I mean, I would just pull this part of paper and as in a torque. So if I do such coordinate system, I can resolve it thus, redefine it as this line. See, after doing that coordinate system, this horizon line would appear something like this. And then that line of singularity, the white line of singularity would actually appear something like this. This is not CT, this is some parameter T which has T in its definition. So yeah, this is R, right, some coordinate. So yeah, this is called Kruskal time coordinates. So now instead of leaving this open, I mean, instead of just leaving this open, I would, for observing in a large picture, I would want to define a point here which would look like this. I mean, I would just want to see the thing in a large picture detail. I would just define a point here which is r is equal to infinity. Similarly, I would just define a point here where the time is minus infinity. This point over here where time is infinity. Right. And then, so yeah, this part was, that this line was horizon. So in a larger picture detail, this curve would almost look like a line. So give me another check so that. Okay. So this was singularity. So yeah, from this picture, singularity is well defined. Singularity is end of time itself. I mean, at t is equal to infinity, singularity is the end of time itself. So right, this would be this. So this is called the Penrose diagram. See, now if I would like to, if you can observe a kind of, so this is black hole, you know that. And we also know that why we defined this region, because we wanted to keep this time cone invariant in all of the graph. So you can easily observe that. See, say take the same friend, again throw him. So it's like when you reach near horizon, it would be, time cone would be like this. And when he's at the horizon, I mean this line, this would be the time cone. When he is little inside the horizon, all of his future cone points inside the black hole. Right? This is clear, right? So now if you could, so I can just say that whatever enters the black hole can never ever come back. Because when you are at horizon, when you enter inside horizon, none of your future events, none of your region of your future cone points in your universe. This is your universe, suppose. When you enter horizon, none of the region of your future cone as a region of your universe. So that's what, so we can just say simply that anything which would enter the horizon, I mean the black hole, would never ever return to our universe, right? So the similar analogy, you can, if you can observe here, the same similar kind of region, but it has an exact opposite characteristics. I mean, the thing is, consider this part. So whenever anything from this part comes here, we can see that it just acts opposite to it. I mean, whatever, you can just send signals, objects from this region to our universe, but we cannot we cannot from our universe go back into that region. I mean, the thing is, this acts exactly opposite to black hole. I mean, anything from our universe to this region, nothing can go, because see, if you draw any point here, your future cone, all of your future cone only lies in your universe. Only the past cone lies in that region. So it means that you can just send signal and objects from this region to universe into our universe, but none of the signals, we can send none signals or any object from our universe to this region, right? So this region kind of behaves very exactly opposite to black hole. I mean, I would want to name this as white hole, right? Now if you are keen at observing, you can kind of see, I'm not just drawing this so that it looks good, I mean, to complete the diagram. So the thing is, these regions are actually the solutions of Kruskal time coordinates. So you can see this, there is a exact symmetric region, symmetric to our universe, similar to where that from this universe, from this region, you can send anything to black hole, but none of the things which enter black hole can come back. So this is a similar thing, that any signal or object can enter this region from the white hole, but any signal or object cannot be sent into that region, white hole. So this this region acts very symmetric to this region, right? So this is universe. I would like to name it as parallel universe, right? So at last, I mean, this is the horizon of the parallel universe and then the singularity. So yeah. So at the last time, just do this to your friend. I mean, come on, for the last time. Your friend is here, you are there. No, take two of your friends. Take one friend here, one here. So you just throw them into the black hole symmetrically, I mean, from this direction, from that direction. So there might be a possibility that they may meet somewhere inside the black hole, I mean, in the singularity. So right, this was the whole idea of what our universe, parallel universe, black hole and white hole was, and these regions are actually the solutions of Kruskal time coordinates. Right. So from this part, I would like to end this session. So yeah, thank you so much for coming to this. So any doubts so far?
Any type of